Hello guys, and welcome to another calculus video. Today we're going to be evaluating this awesome limit. The limit as n goes to infinity of 1 over n squared times the natural logarithm of h of n, where h of n is the hyperfactorial function, which is represented by this product, over n to the n times n plus 1 over 2. So overall, an amazing limit. I absolutely love the hyperfactorial function because it seems like something that you could never use for anything at all, but it actually works out really nicely in this limit. So yeah, let's go ahead and jump into it. Before we do, I just want to discuss the hyperfactorial function because this product notation is kind of confusing. But basically, h of 1 is just 1. Then h of 2 is going to be 1 to the 1 times 2 to the 2. H of 3 is going to be 1 to the 1 times 2 to the 2 times 3 to the 3, and we just continue on, so on and so forth like that. And that's what the hyperfactorial function is. So let's go ahead and start evaluating this limit. So the first step to evaluate this limit is pretty simple. We're just going to substitute in the definition for the hyperfactorial function. Now, the next step that I wanted to do when evaluating this was to just bring in this n squared as a power because of the natural logarithm, and then simplify this because then this would become n to the power of 1 plus 1 over n all over 2, right? But the problem is this is a little bit nasty to deal with because we can bring this limit inside and evaluate it directly, and we would just get square root of n as our answer. But that actually doesn't end up working out, and it makes it much more difficult to solve the actual limit in the end. So what we actually are going to want to do is try to combine this product in the top with this in the bottom. And there's a very simple way to do this. First, we have to recognize the significance of n times n plus 1 over 2. Now, hopefully, many of you have seen this before and recognize it from somewhere. And the reason for this is actually a very important identity. N times n plus 1 over 2 is equal to the sum from k equals 1 to n of k. You know, when you're just summing up consecutive integers. And so that's the important step, the important step that's going to let us evaluate this limit much more easily. So if we go ahead and substitute that in as well, we're going to end up with n to the sum from k equals 1 to n of k. And if you'll notice, that just means this n to the 1 plus 2 plus 3 plus 4 dot 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 all the way to n, right? And another way to write this, because up on here we have a product and down here we have a sum. We want to turn that sum into a product. We can also write this as n to the 1 times n to the 2 times n to the 3 times n to the 4, right? And so we can actually transform this into an infinite product right here. The product of n to the k. And then, as you can see, if we go ahead and take a look at this inside bit one more time, we're going to have the upper product, which is going to be 1 to the 1 times 2 to the 2 times 3 to the 3 times 4 to the 4 over n to the 1 times n to the 2 times n to the 3 times n to the 4. We can actually just match up these terms and factor out these powers. So we can write it like this, 1 over n to the 1. Actually, I'll do this on a separate line because that looks kind of wrong. Write this as 1 over n to the 1 times 2 over n to the 2 times 3 over n to the 3. We can make this one big infinite product. So I'm going to go ahead and erase this. So we can make our limit, the limit as n goes to infinity, of 1 over n squared, ln, of one product, and that one product is going to be the product from k equals 1 to n of k over n to the k. And if you also know the properties of products, if the products have the same index and the same bounds, then you can, and you're dividing them, you can just divide the terms of the product. Now, we're going to do one of my favorite tricks for evaluating both infinite products and infinite sums, actually. And that's that the natural log of a product of something is the same as the sum of the natural log. And so we can see this because on the inside we're going to have just ln this, right? But because of the products of natural logs, this is the same, or this is equal to ln 1 over n plus ln 2 over n squared plus ln, and so on and so forth, right? Because we can expand natural logs out in that way. So let's go ahead and convert that into a sum. So as we said, this was ln 1 over n plus ln 2 over n squared plus ln 3 over n cubed, and we could go so on and so forth. But if we just use our sum notation, this is going to become the limit as n goes to infinity of 1 over n squared times the sum from k equals 1 to n, since our last term will be ln n over n to the n, right, of ln k over n to the k power. And now, since this k power, we can just bring this to the front, right, because of the properties of natural log. And so we'll end up with the sum from k equals 1 to n of k ln k over n. And the nice thing we can do here is we can take this 1 over n and bring it inside here. Now we have something only in terms of k over n. And if you notice right here, we actually have the definition of an integral. Remember that the definition of an integral from 0 to 1 of f of x dx is equal to the limit as n goes to infinity of 1 over n times f of k over n summed from n equals 0 to infinity, from k equals 1 to n, or from k equals 0 to n minus 1. In this case, we have k equals 1 to n, which is good so that we don't have that natural log. So really, we're taking the integral from 0 to 1 of, if we just replace k over n with x, we'll end up x ln x dx. And of course, this is really the integral from 0 plus. It's a limit, but we don't need to really worry about that. So I'll just keep writing it as 0. We can just do integration by parts on this integral, and we will get x squared over 2 ln x, evaluated at 1 and 0, minus the integral from 0 to 1 of x over 2 dx. Now at 1, this is clearly just going to be 0, and at 0, we'll have a nice limit, which we can evaluate using L'Hopital's rule. We'll end up with 1/2 limit as x goes to 0 of ln x over x squared, or over 1 over x squared, sorry, which is equal to 1/2 times the limit as x goes to 0 of 1 over x over negative 2 over x cubed. If we just bring that x cubed to the top, we'll see that this is just x squared over negative 2. And so this is just going to go to 0. So this will also not matter, and we don't need to worry about this term. So we just have negative the integral from 0 to 1 of x over 2 dx, which is just negative 1/4. So a pretty cool result from an amazing infinite sum. Actually, I would like to say that I kind of got the inspiration from this video from a black pen red pen video, both on his video from the hyperfactorial and a similar limit that he did where we ended up with the integral from 0 to 1 of ln x. So anyway, I hope you guys enjoyed the video. I had a lot of fun with the only time I've ever used and probably will ever use the hyperfactorial function. And yeah, hope you guys enjoyed the video, and I'll see you next time.